cryptographic architecture for confidentiality and security in digital transactions. The digitization of money and the adoption of distributed networks have unlocked new possibilities for financial systems. Yet, one fundamental challenge remains: how to guarantee immutability and auditability of transactions in a blockchain environment without compromising user privacy. HARPO addresses this dilemma. It is a technology built on modern cryptographic primitives, ensuring that every transaction is valid and verifiable, while sensitive information about sender, recipient, or amount remains confidential. Technical transaction flow with HARPO 1. Initial scenario: Pedro wants to send 20 reals to João's digital wallet. He only holds a 50 reals note, represented as a digital token, or UTXO unspent transaction output. 2. Validation and authentication before the transfer can occur. HARPO executes cryptographic verification of the note, checks that the UTXO is valid, using proofs of authenticity that prevent double spending. Commitment creation. The note is bound to a cryptographic commitment, ensuring integrity and preventing tampering. Technical detail. Each transaction generates a commitment hash that references the asset. This commitment is stored on the distributed ledger. 3. Transaction execution. Once authenticity is confirmed, HARPO performs a splitting operation. The 50 reals note is consumed, marked as spent. 2. New outputs are generated. 20 reals assigned to João, 30 reals returned to Pedro as digital change. This mechanism resembles the UTXO model used in Bitcoin, but is enhanced with additional privacy layers powered by zero-knowledge proofs. ZKPS, perspectives of each participant. João recipient receives a new UTXO worth 20 reals in his wallet. TIS transaction, history reflects the incoming transfer, confirming the credit without exposing the underlying note structure. This UTXO can be spent later, preserving the fungibility of digital money. Josepha network observer. As an external participant, Josepha cannot access transaction details. What she sees on the ledger are only encrypted metadata, commitment hash nullifiers, that indicate which notes have been consumed. This ensures transparency. She knows a valid transaction occurred, while keeping sender, recipient, and amount hidden. Technical detail nullifiers serve as public markers, preventing double spending, but they do not allow reconstruction of transaction details. HARPO's technical differentiators. Confidentiality via ZKPs. Zero-knowledge proofs. Proves protocol rules are followed without exposing sensitive data. Example, proving that Pedro had sufficient balance without revealing the full composition of his wallet. Extended UTXO model inspired by Bitcoin and Zcash architectures. Each note is represented by a commitment and, when spent, produces a corresponding nullifier. Auditable and distributed ledger. All transactions are immutably recorded. Verification is achieved through proofs and nullifiers, not through raw data disclosure. Automatic digital change. The splitting mechanism enables digital notes to be fractioned into multiple outputs, similar to physical money handling. Scalability plus privacy. B-SUDE. Unlike traditional public blockchains where sender, receiver, and value are transparent, HARPO ensures fungibility and confidentiality, while maintaining global ledger consistency. Why this matters for developers, system architects. HARPO enables the design of payment solutions that balance regulatory auditability with end-user privacy. Blockchain engineers. It demonstrates the practical implementation of commitments, nullifiers, and ZKPs in digital money systems. Security specialists. HARPO creates a model resistant to double spending, replay attacks, and network analysis. Conclusion: HARPO demonstrates that two seemingly opposing principles can coexist. Transparency. Through immutable, distributed auditable records, privacy, via advanced cryptography that protects identities and transaction amounts. Each transaction is more than just a ledger entry. It becomes a mathematical proof of trust, legitimate, secure, and confidential. The future of digital money will be shaped by hybrid architectures like HARPO, acting as the invisible mediator between auditability and confidentiality.